Now that we have a little bit of experience using L'Hopital's rule to evaluate some indeterminate form limits, well, we find that we can't use it in many other situations, at least not immediately. So one case of this to consider is indeterminate products. For instance, what happens when something that's really small, close to zero, is multiplied by something that's really big, infinity? Which wins in that case? Or what if we have something like a difference of two large numbers? Infinity minus infinity. Which one might win in that case? Or there's also indeterminate exponential forms. Something like 0 raised to the 0, infinity raised to the 0, or 1 raised to the infinity. A lot of these, it really depends on which direction you're coming from, or what is more dominating as a behavior. For instance, 1 raised to the infinity, it probably makes sense that just thinking of 1 multiplied by itself over and over an infinite number of times is just 1. But what really has to be more careful of something like that is which direction of 1 are you approaching from? For instance, something that's close to 1, like 0.99, raised to a very large number, actually goes towards 0. While something like 1.01, just a little larger than 1, well, anything larger than 1 multiplied over and over by itself gets really big. Maybe it takes a long time for these results to occur, but either one of those is an equally likely result. So this video is meant to deal with all those other indeterminate forms and ask, how do we figure out their end behavior? And the answer does come back to L'Hopital's rule. Starting with a product, one thing we could do is consider two things being multiplied like f times g. And assuming they are in some indeterminate form, like large multiplied by small, maybe it would help to rewrite them in fractional form. And one way to do this, again using algebra, is to consider something like this. Leave one of the expressions alone, but take the reciprocal of the other expression. So in this case, f divided by 1 over g. Or if g was the function you'd rather leave alone, then we just take the reciprocal of f. We know from our simplification of fractions that these will simplify to just f times g. But perhaps it's easier just to look at this form so that we can apply L'Hopital's rule. So let's see that in action. So let's consider the example of x times the natural log of x and what happens as x approaches 0 from the right. Notice we have to put that quantifier on because x approaching 0 from the left would make natural log undefined. So we just have to make this limit so it actually exists where we can plug values in. But looking at this, we're going to have something that is 0 for x times, well, what happens to natural log of x as x approaches 0? Remember the graph of natural log has a vertical asymptote at x equals 0. So actually it goes towards negative infinity. This is still the same as this indeterminate product form. It doesn't matter if infinity is positive or negative. It's still an indeterminate form. So if I want to use L'Hopital's rule to help figure this out, we'd rather rewrite this into a form that can be used with L'Hopital's rule. But remember, it still has to be an indeterminate form for L'Hopital's rule. So, as the algebra says, we could take natural log of x, maybe let's leave that one alone, but let's take the other function, x, and take its reciprocal. So we get natural log divided by 1 over x. And notice, well, the top is still negative infinity, but the bottom, as x approaches 0, 1 over x also gets very large. So we actually do have our other indeterminate form of infinity divided by infinity. So if we want to apply L'Hopital's rule to this, still the same, limit as x approaches 0 from the right, and the derivative of the top is just 1 over x. The derivative of the bottom is going to be negative 1 over x squared. Remember, this is x to the negative 1 in the denominator, so again, using our power rule, is how we get this result. And if we were to leave this as is, this would still be an infinity divided by infinity indeterminate form. But we can simplify it. So remember, algebra will help us after each application of L'Hopital's rule. And if I simplify both of these fractions down to one overall fraction, I actually get the expression just negative x, which now that's a nice simple expression, and there's no fractions. This is certainly continuous at 0, so I can just plug 0 into this, and the answer is 0. So in this case of 0 times infinity, something really small times something really big, it turns out the thing that's really small kind of won, and overall the limit goes towards 0. As another product example to consider, let's look at this limit as x approaches negative infinity of x times e to the x. So same, just to confirm that this is an indeterminate form. Well, x is just going towards negative infinity, so that replaces that term. And e to the x, well, notice this is the exponent is going towards a really large negative number. So that means this is going towards 1 over e to a very large positive number. And yes, that is something that goes towards 0. So we do have negative infinity times 0, this product indeterminate form. So again, as the problem did before, let's rewrite this as a fraction, as a quotient instead. Here I've chosen to rewrite e to the x into the denominator of this expression. And actually this is the one correct way to do this, so we'll see later why the other direction probably would not have worked out very well. But still looking at this and just making sure that we can apply L'Hopital's rule, numerator goes towards negative infinity, a very large number in the negative direction, and in the denominator it'll be e to the negative infinity, but that's a very large number, so we do get infinity divided by infinity form, so L'Hopital's rule can be applied. Okay, so we take our derivative of the top and the bottom. Derivative of x is just 1. Derivative of e to the negative x. Chain rule says a negative will show up in front. But now we've just got 1 divided by a very large number. Because if we take negative e to a negative infinity, so again that's a very large number going on there. This is 1 over large, giving us overall 0. And there's our answer. Back to the other form, if we would have made the decision to make x as the denominator function, we would get this instead, and this would still give us a 0 over 0 form, so we could apply L'Hopital's to this. The problem we hit, though, is that this ends up being an infinite cycle. So notice the numerator stays as e to the x. The denominator is going to be negative 1 over x squared. And this is still a 0 over 0 form going on. And if we just keep doing that, the numerator is going to stay as e to the x. The denominator, well, it's going to be just negative some number times 1 over x to the n. When you keep taking derivatives of 1 over x to the n, you just keep getting a denominator term that shows up over and over. We wouldn't have received any new information because this would have stayed 0 over 0 no matter how many derivatives we took. There are other examples of this showing up, and sometimes they're a little tricky to see, but I guess one rule of thumb to say is if you ever come across some endless cycle, like after 3 or 4 derivatives, it still is not revealing any new information to you, try switching the other function as the denominator function and see if that makes it better. Lastly, for this video, we'll talk about the indeterminate form of infinity minus infinity, an indeterminate difference. And we'll start off with this example of secant minus tangent. These are two functions that, yes, if you plug in pi over 2 into this, and specifically from the negative direction, this does give you a large number minus a large number. So we're stuck with wondering which one wins. Is the first number bigger or is the second number bigger? But we can't apply L'Hopital's rule to this because it's not in fraction form. And this This doesn't really have a trick like the product does. The best we can do is to hope that there is a way to write these as fractions and then combine those together as such. So in this case, it does work out that secant and tangent both have alternate forms that we can write them in. Secant, well, that's 1 over cosine. And tangent, that's sine over cosine. So rewriting into these fractional forms gives us this idea that, oh, they have a common denominator. So we should be able to combine them into one common denominator expression of cosine on the denominator. And on the top, it would just be 1 minus sine of x. Now, staring at this, well, sine of x, as we approach pi over 2, that does go to 1. So it's going to be 1 minus 1, or 0. And the denominator, cosine of x, cosine of pi over 2, is also 0. So we do have an indeterminate form of 0 over 0. So this means L'Hopital's rule can be applied. So if we redo this limit, as x approaches pi over 2 from the left, 1 minus sine of x, the derivative of that expression will be negative cosine of x, and the denominator, cosine of x, will be negative sine of x. Here we'll see the negatives cancel each other off, and cosine of x is 0 when pi over 2 is plugged in, and the denominator is 1 when pi over 2 is plugged in, and so we get the answer of 0. Both of these expressions were matching each other in how large they were. This example doesn't really reveal much in terms of how we would deal with any general expression of infinity minus infinity. The best we can hope for is that there is some alternate version of fractions that can be used to rewrite those functions and combine them into a single fraction. So again, that's the key throughout this entire section, is that L'Hopital's rule only applies to indeterminate forms of 0 over 0 or infinity divided by infinity. In the next and final video for this section, we're going to discuss the indeterminate powers that we saw at the beginning, 0 raised to the 0, and see what strategies we might use to apply to that.